Good afternoon. Man, you can hear, wow, that's great. Good afternoon, I'm Mark Kleinginna, and I hate being the panel between an audience and lunch. That's really bad. But I think being the panel after lunch might be even worse, as we're all kind of tired. Yeah. And I'm headed toward my afternoon nap, and I can say that today because it's my birthday today. So I'm getting on a little bit here in years. So here's my advice. Stretch, do some jumping jacks, get ready for an extraordinarily scintillating panel. Okay, and this is the awesome panel on the science of tens. And I've been involved with this project for 3 years. It's possibly the proudest achievement or involvement of my professional life, which is actually longer than the lives of 2 of our panelists. The audacity and scope of this project is quite honestly inspirational. I could not be more proud than to be associated with the team that's up here and the extended team which has been assembled. So as we walk through this, these folks are going to share some very, very important and interesting information. Think of questions, and think of questions that you have for these folks. They really want to answer them. I have questions for these folks, but I don't really want to listen to myself anymore. I want to give them the opportunity and you guys the opportunity to form a dialogue. So let's do that, and let's really try to figure out how we continue to make this research move forward and how we continue to promulgate what is such an important solution for the climate. So with that, I'll give you Isabel.
Good.
Hi, everyone. Thank you for coming after lunch. My name is Isabel Varela. I'm with HEET. HEET is an organization with a mission to drive an ethical thermal transition. And some of you in the room may be familiar with the work that HEET does, but what I often find is people are not familiar with the work that HEET does in terms of research related to these geothermal energy networks. So that's the story that we want to tell you today. So HEET leads a research consortium that is focused only on the learning and optimizing geothermal energy networks. It is funded through a grant from the Massachusetts Clean Energy Center. And what we mean by geothermal energy networks, just to clarify, is a single pipe ambient temperature loop connecting buildings with ground source heat pumps to provide heating and cooling. And because it is funded through the Massachusetts Clean Energy Center, it uses data from the demonstration projects in Massachusetts. But really, the learnings, the tools, the applications are applicable for all geothermal networks, regardless of the state. So here, a little bit to show you what are the organizations and what are the areas of work. We will go through them in the presentation. But basically, we have about 7 research organizations, including 2 national labs, LBNL and NREL, and we have various universities, Boston University, UMass Lowell, University of California, Berkeley. And there are different areas that each one of these institutions focuses on. So first, how is this project organized? This is a very high-level organizational chart, if you will. At the center of this research project are the data from the demonstration projects in Massachusetts. So the idea is that all the research gets anchored or validated with those data sets. And these are the same data sets that Jamie Van Nostrom, the chair, referred to this morning. And then we're developing different tools. So these are modeling tools that are meant to be accessible and open source. And they are, for example, for the technical modeling of these systems, but also the economic modeling, how to, as these systems get financed, what is the cost to the customer, et cetera. And the idea is to study what is the impact of these systems in the entire state of Massachusetts. So if you were to deploy them, what is the impact on a number of different factors, including health, the environment, costs, equity, etc. So it's a research project that is focused on geothermal energy networks, but within that, it looks at many different aspects of it. So the data that we're using, as I mentioned, are these demonstration projects in Massachusetts. The first one is the Framingham site that is already operational right now. The second one is the Franklin Field from National Grid. That one is in the design phase right now. And the third one is a second loop in the Framingham site that HEET has been involved with and got a grant from the Department of Energy for the design phase of that project that was completed last year. So what is HEET doing in terms of data acquisition? What HEET has been doing in the Framingham project, the one that is already operational, is we installed fiber optic cable in 14 of the 90 boreholes throughout the 3 different bore fields to monitor the temperature in the subsurface as these systems are in the commissioning stage and as they become operational basically throughout the lifetime of the system. So right now, we have data starting from August of last year. Now, the commissioning process has been throughout several months, so all of the buildings and the very last bore field actually went online just last week, very recently. So a full year for the entire system to be online will be more or less a year from now. But we do have data from August of last year throughout the commissioning stage. And here, what I'm showing you is actually 3 of the boreholes that start in August and go. This one is through February, but we actually have it going on, in real time. And as we expect, we have an increase in temperature in the subsurface in the heat at the tail end of the heating season, and then cooling. In the cooling season, and then cooler temperatures in the heating season. And that temperature change that we see is about 4 Celsius from the average temperature of the subsurface, that is about 12 degrees Celsius or 55 degrees Fahrenheit here. So we, just as we expect, we're getting this sinusoidal curve. And the idea is really to study maybe if there is any potential drift as the years of operation go on, it can be detected, and also to study the thermal storage in the subsurface. And my colleague Eric Juma will go into more detail about this part of the project. Another aspect that the project focuses on is on the development of these tools that are accessible. So, for example, one of the tools that is generally used for designing these systems is Transys, that many of you may be familiar with. Now, usually only engineering firms have access to it, and even within those firms, only specialized teams, work with it. So the idea was to create a tool that is more accessible. It's written in Python, it's open source, and it will be basically on our website. It's already functional. It doesn't have a user interface right now, but it works. And this tool is built by NREL. And so in the modeling part, there's teamwork between NREL and LBNL. LBNL created this full physics model that is meant to capture all the complexities of the system and is used to validate the more simpler reduced order model tool that is the one that was created by NREL, that is the one that we actually make available to everyone. So that those modeling tools by NREL have 2 aspects: the technical aspect or engineering aspect, and also the economic aspect. And my colleague Rebecca will touch more on that in a minute. But I wanted to share here an example. So this is on the technical aspect. If you have on the x-axis the buildings along the loop, and you have in the summer as a temperature, as you go from building to building, the temperature goes up. And as you get to the boreholes, that's where the temperature comes down. And again, as you go from building to building, it increases. And then again, when it reaches that other borehole, it comes down. So here you see the locations of the different boreholes. And in the winter, as you expect, then it's the other way around. It gets cooler as you go through the loop and then warmer as you get in the borehole. So the idea is really that as you're building, as you're doing feasibility studies or in the early stages of building a network, you can play with this tool and look at, okay, if I add more buildings or if I add more boreholes, what does that do to the temperature in the loop? What does that do to the coefficient of performance of the system that will then impact economics, as it was mentioned in one of the panels earlier on with a graph actually by Ania Camargo. So these tools are meant to help you ask questions about your system. Okay, so other aspects that the research group is looking at is, impact on emissions, but also on the electric grid, on costs, as we mentioned, on ecology, on health, and on equity. So what happens when these systems are deployed at a large scale? So briefly, the outcomes of a study that was done, impacts on ecology for the Framingham project. So this is work by Nathan Phillips from Boston University. He analyzed 161 trees, and basically he did that before the system was installed in Framingham and after it finished construction, and he found no impact, negative or positive, on the trees, right? And the idea is to continue this work in the early stages throughout the years of this project. Another tool that was developed by Boston University kind of ties into what my colleague Angie mentioned. If you were to deploy these systems at a city or statewide scale, what are the layers of information that you would need to put together, to combine, to make an optimal rollout of these systems? So here is a start of that project. There's a series of layers here. You can see them. Household income, energy cost, natural gas infrastructure, utility providers, etc. So there's a number of factors that you want to take into account and to combine them together with an algorithm that you can then modify to make an optimal decision. So these are tools that are being built right now, and this product is already available, these dashboards. And we will share all of this towards the end, how you can access it. My colleague Angie already talked about the feasibility program in Massachusetts, so I'll be very brief. But basically, 8 communities were funded through this research program to do feasibility studies in their communities, and 4 communities were funded to do site selection and community engagement. And some of the highlights of this work is early community engagement with municipalities and community leaders is very important to impact the momentum of the project, and also that policy and regulatory hurdles can be perceived as a challenge for those non-geothermal experts. Move on. The idea is, as I mentioned, to expand these studies at a statewide scale. And for that, we will be using the same tools, for example, the NY-GEO tool that also calculates the economics and it calculates the impacts on the electric grid for one particular system. And then this can be expanded, for a city scale or statewide. In terms of deployment, one thing that we want to do is to maximize learnings. So how can we maximize learnings from the systems that are already implemented? One thing that we thought is if we have a database where we can share information in a systematic way about all of these systems, and this is already available, it's live, and what we want to do is to populate it now with data. So if you are a developer or a utility that are working on these projects, then we'd love to talk to you to populate this database. So the idea is basically if you're a community that is doing a feasibility study and you want to know what is the size of the main pipe that was used in Framingham, you could go ahead and look at it, not only in Framingham, but in all the other projects that are in the database. You could look at the same parameter across, and it would help disseminate the learnings. So it's a public data bank to inform and facilitate the future developments. It is hosted in the Harvard Dataverse so that it can be there in perpetuity. They have the infrastructure to do that with the databases. And we often get asked the question, if there's a project that is outside the US, can we put it in there? Yes, we can. These, to give you an idea of the type of parameters that we're capturing information about buildings, about boreholes, about the system performance, about the subsurface, about costs, and even about demographics. And as we close here, I wanted to share that HEET is very involved in the second loop. We received the funding for the design phase of that second loop, and also we were selected for the construction phase of that second loop. And we hope that that project moves forward. This is a grant by the Department of Energy. And with that, I would like to share that on Monday, our research team is going to get together and share all the learnings from these last few years, including all the tools that I shared. It's the first time that we do an open day for this consortium. You're all invited to attend. Here is the registration link and agenda for that day on April 28th. If any of you here happens to be in the Boston area, we would love it if you would attend in person. Please, reach out to me after the panel. Here's the registration for the live stream. Thank you. And I'll pass it on to Juma.
All right, hello everyone. Y'all hear me okay? Good. My name's Eric Juma. I'm a technologist at HEET, and I've been leading the operations on site in Framingham to install the distributed fiber optic sensing system. So I'll give you some background on the Framingham project. This project, it's Eversource's project. It's a single pipe ambient loop that's about 1 mile long. There are 90 boreholes split across 3 bore fields, and you can see them there. One of the bore fields, the one in the top left, is has incline bores. It's an incline bore field, and the other 2 are vertical bore fields. There are 375 tons of thermal load on this system, and there are 36 buildings serving about 140 customers, one of which is a large school building, which you can see in the top left, right next to the incline bore field there. So what is distributed fiber optic sensing? If you're a normal person and are unfamiliar with this technology, your mind is about to be blown a little bit here. Distributed fiber optic sensing is a technology that we can use to measure the temperature along the length of a borehole or a horizontal loop as well. And it works by using almost a typical fiber optic cable that you would use for networking, but instead of the cable transmitting binary data, it itself becomes the sensor. And this device called the interrogator shoots a little laser pulse down that fiber and measures the reflections of light coming back up the fiber. And based on the time it takes for these reflections to return and the frequency spectrum of light that it receives, it can deduce, using some crazy math, the temperature along the entire length of that fiber. So using the device we're using this in this project, we can get about a 1 meter spatial resolution and a 1 degree Celsius temperature resolution. So pretty cool technology, but why actually go to the effort to install it in the system? And this is a question you may really have running through your mind as you tape hundreds and hundreds of feet of fiber optic cable to YouTube's, as I did. So it's a typical bore field monitoring solution is measuring the temperature of the fluid as it enters the bore field and the temperature of the fluid as it exits the bore field, giving us the delta T. And you can learn a lot from this, but the DFOS system gives us the actual borehole temperature along its length, as I was saying. And if you have it installed in a borehole that is not connected to the loop, such as a test borehole that's orphaned, you can get a profile of the subsurface that you couldn't get from measuring the delta T, and that's where things get really interesting. You can use this to detect thermal drift over time and measure it. You can even see groundwater flows as the this graph on the right here. You would see like a jump off, say, to the right if there are groundwater flows at a certain depth. You can also use it to quantify thermal storage. And for the LeGUP project, it's beneficial to us because we're developing different models, including subsurface models, and we can use this data to test the models and validate them and integrate with them. So it's going to be really interesting to see how the subsurface conditions change over time as this thermal network operates. So a little bit about this actual project. The DFOS installation was a collaboration between Eversource, HEET, and SOGA Research Group at UC Berkeley, who are the actual DFOS experts. And a big shout out to all of the drillers we worked with and contractors. I think Celsius, maybe someone from Celsius is here, at least in the conference they're here. And they were really helpful and collaborative on site as we were trying to install this technology. It gets complicated, so we're really grateful to them. We instrumented 14 boreholes across the entire system, with most of them in the incline bore field on the left there. We also instrumented the 3 thermal response test boreholes and collected data from the DFOS system during the thermal response tests. And of these 14 boreholes, 2 of them are currently not connected to the loop, but they have DFOS monitoring in them. So those are going to be interesting to look at, so we can get a peek into the subsurface. We experimented with different fiber configurations throughout this project. On the right, you can see like the ultimate DFOS nerd's dream of instrumenting, getting fiber inside the actual YouTube and in between the YouTubes. And this is how we started off during the thermal response testing. But to accommodate the timelines of the drillers and to just make things easier for them, we moved to these 2 models in the middle. Oh, you guys can't see my mouse cursor. That's unfortunate. But oh, so we tried this, where the fiber goes on the outside of the YouTube, and that's great because you can get the temperature going down and coming up, but it requires some pretty precise taping about every 3 feet of the fiber to the YouTube, so it does take more time. So we ended up moving to this model of just having a fiber ideally carefully centrated between the YouTubes, or the YouTube in the middle of the YouTube. And that's how most of the boreholes in this project were instrumented. And on the left here, you can see the double YouTube, which was used in the incline bore field. So they actually used a double YouTube, also known as a quad loop. So because of that, we just had to kind of throw the fiber down there with the YouTube. It's not really possible to centrate it. And you can see the fiber here connected to the actual U-bend right there. So as Isabel was saying, we're just finishing up with the actual installation process. So we haven't dug much into the data yet, but we do have some data here to look at. Interestingly, this is from the inclined bore field, and the inclined bore field was split into 2 platforms, each with those inclined bores kind of coming out in this pyramid shape. So at some point, soon after the system was starting up, they turned one of these platforms off, and you can see the temperature dropping there and remaining stable as the cooling load increased in these early days of the system. Then they converged, and I think at this point they enabled this other platform that was off, and then the 2 platforms are relatively synchronized in the temperature of the boreholes. And as Isabel was saying, you can see the cooling load increasing the temperature of the bore field, and the heating load cooling it down, and that kind of tapering off as the winter ends. This is also an interesting case. At the Rose Kennedy bore field, we have one borehole here that was not connected to the system due to a borehole collision, but we instrumented it. So the temperature is relatively stable as we would expect, but it does start to slowly drift down as time goes on. So it'll be interesting to see where that goes. And this yellow borehole here is just a typical borehole in the system with the temperature corresponding to the loads. So our next steps are to resolve those intermittency issues, sometimes the interrogator dropping off, as you saw, and then just to dig into the data, do an integrated analysis with the SCADA data, whichever source is going to provide to us, analysis of thermal storage and thermal drift as the system continues to operate, and the integration with the other models in LeGUP, the full system model and the subsurface model. And we're planning to share all of this data through the HEAT databank that Isabel mentioned earlier. And we are instrumenting 2 more geothermal network projects in Massachusetts. One is the National Grids project at Franklin Field, which we'll be installing DFOS in, and then the Framingham second loop, the loop expansion of this geothermal system. So looking forward to all of that. If anyone is interested in this research, has any insights you're hoping that we might find from this data, or any ideas of how it could be helpful to you, come talk to me, or you can find our contacts on the last slide at the end of the presentation. So thank you, everyone.
Hello, everyone. My name is Rebecca Brenneis, and I am a research scientist at HEAT. And I'm going to be talking a little bit more about the core modeling aspect of the project. So modeling is at the core of LeGUP. It informs all of the downstream objectives. Modeling is critical to reducing costs and electrical grid impacts and increasing efficiency of systems. Models are informed by the data we collect, which improve the models. As the systems are the most efficient with the minimized grid impacts, the broader impacts of the systems can be quantified and modeled in turn, maximized and modeled in turn, which just creates the groundwork for scalability of the system. But models are only as successful as transparency and data access allows. So as LeGUP just collects as much data as possible to inform the models, they improve. But we are always in the market for more data, both for the data bank or in any capacity to improve models going forward. So if anybody in the room has data, I'll just third the request on the part of the panel to make that data accessible to us, and just please reach out. We're going to talk today about a model in more detail that was developed at the National Renewable Energy Laboratory in conjunction with HEET under the LeGUP project. And the particular model was conceived as a decision-making tool to put geothermal energy networks on the list of potential solutions for feasible energy future. So we've heard a lot today about people trying to find economic answers to whether or not geothermal energy networks are the solution for them. They are not a new technology, but they are not rolled out as widely as some other technologies, and we don't necessarily have all the tools that we might want to have so that people can determine, what are the capital costs going to be, what are the levelized costs of energy going to be, how are they going to be able to decide whether or not this is the right solution. And without those, we don't want these technologies to these lack of tools to stop the rollout and scalability of these systems. So within LeGUP, this also helps us understand not only how to make better systems, but how to answer the questions that users need. So this particular tool works for fifth generation thermal energy networks, which are characterized by a single pipe ambient temperature loop that networks a lot of different ground source heat pumps that are decentralized. So these systems are the most flexible solution to serve numerous dynamic loads. They allow the integration of infinite low-grade heat sources, minimizing capital investment and infrastructure required to serve the electric loads. The systems are designed to scale and increase in efficiency as sources are added or connected to additional loops. This makes them uniquely predisposed for scalability, and that's why we're targeting with this particular modeling technology. So we're talking today about the HEATnet model, which I mentioned was developed at the National Renewable Energy Laboratory as part of the LeGUP project. So it is a Python-based open source techno-economic model. It is designed to optimize both energy and cost efficiency, maximizing the feasibility and financeability of these projects. The reduced order physics model captures energy flow and electricity use in the loop, and it fuels a cost estimation and economic analysis model. So we're aiming to take a holistic view of TENS using available standards and evaluate energy potential and cost competitiveness using this model. So here you see a model flow diagram. The blue are the inputs, which you would get based on your system design. And then the reduced order physics model produces a number of energy-based outputs, but in particular, the electric time series data, which feeds into the economic analysis model and then provides the economic feasibility analysis. So we've heard today a lot about how electricity is a component that needs to be examined when looking at the economic financeability feasibility of these systems, where this helps us inform a way of quantifying and talking about the reduction in electric load necessity, which is one of the big positives in the system. And also electricity costs are different than the costs of other heating solutions, if there's gas, for example. And so if we can, show what those actual electricity changes are going to be, we can start talking about what that is going to cost for something like the ratepayer and what a thermal energy price is going to do to something like the rate of return on a project. So that's how the physics model flows into the economics model. So here's a little bit more about the reduced order model. So this is taken from a study that was done to train the model using the Framingham pilot project, which we heard about earlier. So in this example, there are parameters that were fed into the model to train the model, and those were from the Transys design, which included the building loads, the bore field performance data, and the flow in each section of the loop. The model was then used to generate information about thermal loop inertia, heat transfer, and pumping power, in addition to the energy consumption that we talked about earlier. And here is an example of some of the outputs that we can get from the reduced order model before taking in the economic considerations. So this particular example was a quantification of the electric consumption of the system and how it's impacted by the percentage of glycol or the minimum temperature limit on the loop. And so you can see that with additional use of glycol or the higher temperature limit, you're going to have higher energy costs of the system. This is associated with needing more auxiliary heat power added to the system or with more pumping power. And if we can minimize those things, we can minimize that electric usage by the system, minimizing the cost, et cetera. Some other aspects that are not necessarily shown in this figure, but were part of the study, were takeaways were that if you increase the pipe diameter, you can also decrease those energy costs of the system. Or if you add more bore fields, they're obviously going to bring down the energy costs of the system because you have new generation sources as long as they're right-spaced for the system. So now talking about the economic model, once you have this time series electricity data, it can be input along with some assumptions about capital costs and local electricity costs and pricing, which then the model runs and spits out a number of economic parameters, the localized cost of energy, the net present value, the internal rate of return, and then additionally the thermal energy price and building energy payments by time step. So the model generates the levelized cost of energy, the IRR and the NPV, and then it finds a thermal energy price and it checks for a deterministic IRR. And if the thermal energy price can meet that IRR, then that's the solution. If the TEP is negative or that IRR isn't as designed or desired, rather, then it continues to iterate until it finds a thermal energy price. And then when you have the thermal energy price and you have the building energy payments by time step, you can start looking at those for cost competitiveness, financeability, and how is this going to look in a greater picture as, is this the energy solution that's going to be, either the best economically feasible or can it be economically feasible enough given the other benefits of the system? So here are some decision use cases. So let's say you have a system that has, given land use issues. So for instance, like what is the energy density of the buildings on your system? What is the sort of energy generation per, foot of pipe that needs to go into the ground? And then what are the particular building load look like? Do you have sources in your system that, reject heat? Do you have a lot of grocery stores? Do you have a lot of waste treatment plants that can provide heat to the system? How do those particular aspects influence the overall economic output? So if you are a small community in Vermont and you want to know whether or not your three system, whether or not the heat from one to another would generate enough electricity offsets to be really cost competitive, this would be a way of trying to answer that question. And we also have answer questions about existing electricity economics. So if you are looking at two different systems that are in areas with different catchments and different utility electricity costs, how are those particular costs going to downstream look at influence the financial picture of your systems? And then additionally, when you have thermal source potential, what are your, if you're looking at a geothermal system, what is the bedrock level? What is the, aquifer situation? What kinds of technologies can you either drill or pull from to add thermal resources to your system? And then from there, what does the energy cost consumption look like as you make those changes? And how does that affect the bottom line in the end, the financeability of the system? So key takeaways is that this is an open source technology. I don't know that I iterated that enough, but this is a tool that can be put in the hands of anyone who wants to look at the overall impact of their potential system. So this is a lot of models that currently exist are, I think it was mentioned earlier, in the hands of a small number of people with a lot of access and technical expertise. And not necessarily always designed to address this particular technology. So how do we try and start answering the questions that people have been posing today? And how do we put a tool in their hands so they can start answering these questions? And that is the goal of HEATnet's in a broader aspect beyond necessarily just how do we gain information for LeGUP. And the next steps are that we are currently working on the user interface. So the model works, as Isabel mentioned, it runs and we can collect data from it, but at the moment it is not super accessible if you don't do a lot of coding. So we're in the process of developing all of that and hoping to launch that within the year. So if you want to find out more, again, please, here's the QR code. Please attend our to find out more about the LeGUP annual meeting, which is on Monday, where we are happy you'll be able to hear from the NREL modelers themselves. And if you have any information that you could share with us, data-wise or other, we're happy to hear from you. So with that, I will hand things over to Mark.
All right. Thank you, Isabel, Eric, Becca. Really appreciate all that. My questions are boring. So if you guys have them, please stick your hand out for the microphone. Anyone? Dying up here. Okay. Oh, there we go. There's a gentleman right there. Thank you. You saved my life. I'll slip you the 5 afterwards. Damn it.
Can you hear me? Yeah, there we go. Yeah, I'm Gary Eubank with the Gray Edge Group, Next Step Solutions, and Eubank Geotesting. But back on the economic modeling, on the ground heat exchanger itself, how did you handle the depreciation or the appreciation of the ground heat exchanger?
So that is it's a level of technicality that I don't particularly have the answer to as not one of the modelers themselves. It's something that we can look into, and we'd be happy to get back to you if you can reach out to us. I will throw it to Isabel or Mark, who've been working with the project longer, to see if either of them can speak to it, just to make sure that it, gets the answer.
I'll mention briefly that the reduced order model currently uses a lookup table that was generated by LBNL. So for modeling the subsurface part. So currently that's how it's working. So we need to find right now an independent way of modeling the subsurface part if we don't have a lookup table.
Yeah. Currently, we do not have a process to where we can take a asset that increases in value with time. And so if we put it in the capital costs and depreciate over 10, 20, 30 years, that's not the real cost. It's actually improving. Does that make sense?
I'm not sure. Could you just talk through it with us?
About half the cost maybe is ground heat exchanger and then piping on these systems.
Okay.
It's not normally always the case. But anyway, that stuff that's in the ground lasts us longer than the buildings.
Sure.
Okay. And so when we put it in with the capital cost for the project, you get a 20-year or whatever you want.
Right.
But when you go through that and do that analysis, we have to have a way to recognize that increased value of the ground heat exchanger.
Sure.
You know?
And that's a great point. That's a point that we oftentimes miss when we're doing the economics and net present value of this. We've not gotten specific about depreciation schedules on the way we're doing the economics. It's a very simple sort of straight line 20-year project finance look at it, or 30-year the way a utility would look at gas pipe in the ground. We've not, but there's the ability to replug that portion into the model and do it well. And that's a very, very excellent suggestion as we go to put functionality in it to make this thing, look like it should look. So that's a great point, and we'll take that one back for sure.
I'll mention just one thing related to that, and that we're collaborating with UMass Lowell. They're doing an LCA and life cycle analysis cost assessment and life cycle cost analysis. So both, and this is ongoing work that is not yet ready for sharing, but that's part of it.
Yeah, the life cycle cost.
Yeah.
The salvage.
Right. Go ahead. Yes, sir. You
We're going to say something?
go ahead.
Hi there. I'm Max Shabako with NYSERDA. My question is, I saw that you were saying that with reduced glycol, you could have higher efficiencies on your pumps. But on your website, it says you're using 25% glycol. I was just wondering why you gave that example and why you're using the highest percentage.
So I'll just mention briefly. So those design parameters were selected by the designer, and so he did not participate in the design of that first loop. We do know why it was the 25% glycol is used. It's for antifreeze, given the weather in Massachusetts. At the same time, we also know that there are systems in Canada that use 100% water, and they're even norther and harsher, colder climates. So I think it was a precautionary, is what we understand from the designers and owners of the system, and yeah,
So with that precaution, knowing that the systems in harsher climates are using 100% water, do you think that this system could eventually become 100% water?
I don't know if this particular one, but generally, if we have, examples of other systems that are that have 100% water and are functional and don't have the issue with freezing, then it is likely that other systems in the same area can function the same way. Yes.
Yeah, I think that the point of this is that this allows us to take a very close look at whether that makes sense or not, and potentially we can move the ball in a direction that allows for exactly what you're talking about, right? So that's why this modeling is so important, to actually get answers to that question.
So yeah, exactly. It's to spark those ideas. If we put how much glycol, what does that do to the efficiency of the system? What does it do to cost, right? There's a cost to glycol. So the idea is to have a simple tool to measure that and evaluate, then do we really need it?
Other questions? Go ahead.
Yes, Keith Merle, Morshay. You mentioned that it's open source. Can you tell us what licensing sort of protocol you used, and what does that allow you to do with the software as people are starting to try to help develop it?
Good. Okay, so basically the idea is it's written in Python and it's accessible. So once you, if you are comfortable not using a GUI user interface, then the tool from NREL is available right now, and we can reach out after this panel.
Hey, Jared Rodriguez, Emergent Urban Concepts. To what extent does the HEATnet software iterate on rights of way and system design if, say, you were to, across an entire neighborhood, put in the building energy use parameters? Does it do that in that direction, or is it only you have to put in sort of fixed customer parameters?
So it will not optimize a path for a loop, if that's what you're getting.
So that's fixed in the analysis.
It's what's in the ground as kind of planned out. It will take into account adding or removing loads, but basically the loop is as the loop does. It won't say, oh, we should go over here, or anything like that.
But will UrbanOpt do that or no?
UrbanOpt may do that, but this is not set up to do that type of analysis. This is basically for something that's already been planned and put in place.
We should talk because there's a Dutch software service that can do that.
Mm-hmm. Of course. Great comment. Thank you, Eowyn, for getting your steps in. Appreciate that. People.
Hi, Mike Kingsley with Ramble. I was wondering if the model can predict seasonal drift in temperatures for the bore field, and if you can add, say, components in the model, however simplistic or complicated to deal with that.
I think you could use it for, so if you model, you're not going to see that like after 1 year, but you could model, say, your 10 years of operation under these conditions, and what is the subsurface thermal drift that you would see. And then, then you would probably make a design change beforehand unless you're planning to use that in a certain way.
Hi, Brock Yorty with Geothermal Drillers Association. When we look at installing DFOS in the field and, increasing our data retrieval, Eric or team, what do you see for adoption? What can we get better at doing so that we can install this effectively and make sure that we're using it properly?
That's a great question. It was a bit of a challenge installing it. It's normally been done by Sogo Lab and under more controlled conditions, so we did have to adapt, right? Part of that just comes with experience. Having an understanding ahead of time around the timing changes that are involved with the insertion of the YouTube is really important. yeah, I personally look forward to it being easier the next time, not knowing what I know. And I think that there could be a way that we can publish our learnings on it so that others who want to undertake this can also make those changes to their protocols.
And thank you. And I'll add one thing that, for example, what we were planning to do on the lower project is they actually put it on the RFP for the drillers that this fiber optic cable is getting installed so that they would know beforehand and know what to expect. We've also planned, for example, for the second loop where he does have, more input into how things are done, then to have a training session, very simple, one day with the drillers on how to install this fiber optic cable, before drilling operations start so that everything goes smooth.
The main challenge is just taping the cable to the YouTube as it's going in. So if there was some way, and I don't know if this is realistic cost-wise, but to have a technology that could simplify that process, either a way for some sort of different type of YouTube that had attachment points for fiber optic cable, or a way for it to be integrated into the plastic itself. I'm curious if anyone thinks those things are possible, or if we can continue with the taping method and develop our physical motor skills to increase the rate.
I would also add that I think it's important that we make the case for DFOS to the drillers, right? So you guys tell us, you see this stuff up here, right? Is this valuable? And if it is, then help us do this, right? And clearly it doesn't have to be every time, but if we've got 14 out of 90 instrumented here, we're going to learn a lot, right? Does that help you guys sell what you do, right, out in the field? So I think Brock, it's a great question, but it's a collaboration, right? I mean, when I saw it the first time, I said, well, put the fiber optic in the borehole, right? Just like have it go in it with it, right? That doesn't seem to be possible yet. So we're taping like crazy, right? But then, is that valuable as we're going through this? If it is, well, then help us work together to get that done. So
yeah,
enough from me.
Another thing we'll learn is what are the optimal placements for the fiber optic cable, and what can we reduce the number of boreholes that we instrument and still learn the same amount from it?
So if we treat this like Garrett has talked in this idea of this life cycle and, 80 years, municipal water wells are now, stainless steel and are treated to be 80 years. And we put instrument tubes in municipal water wells all the time for the same SCADA systems and stuff. Right. Those are the same drillers. Yes, everything's a hammer on the job site for us, but yeah, we can get sciencey when we need to.
Right. And I think that's the conversation we need to continue to have this thing evolve, have the business of measuring this evolve going forward, for sure. Thanks. We've got 4 minutes, folks. Come on.
So Amina Camargo with the BDC. So I'm a little frustrated with the timing of it. Right now there are 22 utility pilots that have been filed across the country, and they can use this, like they want to learn from what's happening as fast as possible. So I'm wondering how we can speed up sort of the transfer of information so that the current utilities who are proposing pilots and filing them can include some of the learnings, because it feels like it's not coming out fast enough.
We're here.
Come to our annual meeting next Monday.
No, but I think this is extremely important, and this needs to be done in Utenja, and it needs to be wherever there is legislation or there is staff involved in rolling these things out. You need to make sure that the data is transparent. And oh, by the way, we have a really, really nice data bank that we're putting together that's already been established. And Maryland did it. Maryland said, thou shalt put your data in the HEAT data bank, right? So this is something that makes a lot of sense from that perspective. Is to go ahead and get that done. Talk to your folks at your public utility regulatory commissions to ensure that when these things are paid for by the utility ratepayer, the information that comes out of them is provided somewhere that is open source, open access, and so on. And I apologize. Get a little evangelical up here for that. But talk to your congressman and your utility staff person, right? Talk to these folks. Let them know that that's what you want. What else?
Yeah, it's the best.
Yeah. Are we done? Okay.
Happy court.
Thank you.